Okay, so this is part three of the presentation on hypothesis testing. So in part two, we kind of went over calculating a t-statistic and then using a p-value approach to decide if we have enough evidence against the null hypothesis or not. In this part three, we'll go over another approach which we call the critical value approach. It's actually based on the same ideas. It's just a different way of expressing the same thing in my opinion, right? So basically, it's another way in which we evaluate, right, if our evidence is strong enough against the null. So what is the critical value? The critical value is the numerical value of the test statistic that results in a p-value equal to the significance level. The larger the test statistic, the more evidence we have against the null. So if the magnitude of the test statistic is larger than the critical value, then we will reject the null hypothesis, right? Because any test statistic larger than the critical value will have a p-value less than the significance level. So kind of let's draw some of the pictures again, right, to see how we actually find the critical value, right? So it's a quick critical value. So in this case, because we are looking at a t-statistic, so typically we denote it with t star, right? It's the value of your t-statistic whose p-value is equal to the significance level alpha. So let's draw some pictures again. So again, it's going to be driven by what kind of alternative hypothesis you have. So let's say you have a two-sided test, right? And we draw our t-distribution, bell shape, centered at 0. The value of t star will be such that the area to the right of positive t star and to the left of negative t star, these two areas will add up to alpha. So individually, because of symmetry, each area is going to be alpha over 2, right? Because the p-value is going to be exactly equal to alpha. So what this means is that the area in the middle is going to be 1 minus alpha. How do we find this t star over here? Well, we can type in qt, right? So instead of finding the proportion, we're trying to find, right, we know the proportion, we're trying to find the corresponding value of the distribution. And this percentile is now 1 minus alpha plus alpha over 2, so we'll get 1 minus alpha over 2, common degrees of freedom. That's how we will derive the value of t star for a two-sided test, right? So you kind of realize it's a bit of a reversal of the process, right? So if your test statistic is equal to this t star, then its p-value will be exactly equal to alpha. And if it's larger than t star, right, then, so let's say your test statistic is over here, it's larger than t star, then the shaded areas will be less than alpha and we'll reject the null. So that's what I mean by these are ideas that are linked with one another. So this is a two-sided test. If you have a one-sided test, let's say greater than bell-shaped curve, centered at 0, t star, area to the right here is now alpha, and area to the left is 1 minus alpha. So this t star will be found using qt 1 minus alpha degrees of freedom, right? So it's a little bit different from the two-sided test. If it's a left less than alternative, maybe let me just move this higher up, right? Then your t star is here. By convention, t star is usually viewed as reported as a positive value. So if it's a left, then you put negative t star, and then this area here will be alpha, right? So this value of negative t star will be found using qt alpha df. But due to the symmetry, right, you realize that this value here and that value, they are numerically equal to one another, right? The only difference is that one's a negative value. So negative qt of alpha of df is equal to qt 1 minus alpha df, right, because of symmetry. And by convention, as I said, usually the critical value is reported as a positive value. So typically for a one-sided test, right, this is how we find a critical value by convention. Okay, so some exercises over here, right, find the critical value of a two-sided test. Alpha equals 0.1 with 10 degrees of freedom, right? So with the first example, two-sided test with alpha equals 0.1, right? right? So if you were to sketch the bell shape, two-sided test, right? So each area would now be 0.05 because we have to split 0.1 into 2. And this area has to be, whoops, 0.9, right? Because the entire area has to add up to 1. So basically, T star will be found using QT 0.95, 10, right? Because the percentile is 0.9 plus 0.05, which will give us 1.812, right? So in such a setting, the critical value is 1.812. So if your test statistic is larger than that in magnitude, we would reject the null hypothesis. Second example, one-sided test, alpha equals 0.02. So that's your one-sided test. You want to find T star. And this area here is 0.02. So area to the left is 0.98, right? So in this case, your critical value will be found, using QT of 0.98 because it's 0.98 to the left, comma 55. And if you work this out, 2.104. So that's the critical value in that example. With the last example, you can work on it on your own a little bit. The last example, you should be typing QT 0.99, comma 70, 2.381. Okay, so these are just some worked examples on how to find critical value. So the result, the conclusions from the p-value approach or critical value approach will always be consistent because they're based on the exact same concept, right? Basically the t-distribution, and we know we can find areas under it to find probabilities. It's up to you which approach you want to use, whichever you're more comfortable with. People like the p-value approach because it's a probability measure, so it's between 0 and 1. Whereas the critical value approach, right, it's not, the critical value has no bounds, right? It's not a probability measure. So people like a probability measure because they can think in terms of proportions. So that's one reason why usually in most scientific articles they will report using a p-value. So to summarize the hypothesis test, right? So based on the question of interest, you want to write your non-alternative hypothesis, evaluate how dissimilar your sample is from the null by calculating the test statistic, and then compare your sample with a benchmark, two equivalent approaches. Again, you just need to use one of them. And then write a relevant conclusion for your specific analysis. Okay, so in the next video, I will just go over a worked example to tie everything in together.